So let's take a look at practice problem 4 from module 4. And as always, let's read the problem. So we're told that Earth has an electric charge on its surface, which produces a 150 Newton per Coulomb E field, which points down towards the center of Earth. Estimate the net charge that your body would need to have in order for the electric force exerted on you by Earth to support you. Grammar on that, but that's okay. Estimate the net charge that your body would need to have in order for the electric force Earth exerted on you by Earth to support you above the surface. So what we're saying is that Earth has an E field around it. And because we are near the surface of the Earth, we can take the surface of Earth to be flat. We don't need to worry about Earth being spherical because that is not relevant to our daily lives. So this is going to be Earth. And we are told that the Earth has an E field which points down towards its center. And E is going to be equal to 150 newtons per coulomb. And the question is, what does the charge on a person have to be so that the person can levitate? So this person is going to have some mass and some charge that we don't know. So the mass, I'm going to say, let's just say like 60 kilograms. That's around the mass of an average person. If you wanted to use your exact mass, you could look that up. I'm just going to use this because it's an average. And the charge is what we're looking for. So now the representations we're looking for is a force diagram. So this is going to be a force diagram for our body, for the person. So we start with our dots. We know that the Earth is pulling down with gravity. Let's make that a little bit smaller. So the force, the gravitational force that the Earth exerts on me. And what's balancing that? Well, if I'm not touching the ground, then the only thing that could be supporting me is the electrical force. So the electrostatic force. That Earth exerts on me. And if I am stable, if I am just floating, then those two must be balanced. So I can say the sum of the forces must be 0. And now I want to solve for Q. So because I'm levitating, I don't think that's how you spell levitating. Because I'm levitating, I know the sum of the forces must be 0. I can use my force diagram to set up Newton's second law. So acceleration is 0. So the sum of the forces must be 0. And the sum of the forces is going to be equal to the electrostatic force the Earth exerts on me, minus, because it goes down, the gravitational force the Earth exerts on me. So I know the equations to describe these forces. So we know that because I'm near the surface of the Earth, I can say the gravitational force the Earth exerts on me is just going to be mg. The electrostatic force that the Earth exerts on me could be k q1 q2 over r squared if we were talking about the electrostatic force between point-like charges. Or it can be QE, the charge on me times the magnitude of the E field that I'm in. So which of these two is appropriate to this problem? So I know this is the one I have to use because I'm not given the charge on Earth. So even if I could treat everything like point charges, I don't have enough information to use that. So I have to use this. Because I was given E, not the charge on the Earth. So I can substitute these in. And plug in values. 0 is equal to QE minus mg. QE is equal to mg. So I'm adding mg to both sides. And then Q is equal to mg divided by E. M, remember I said was 60 kilograms. G, we can say is 10 newtons per kilogram because precision doesn't matter here. And E, we were told, is 150 newtons per coulomb. Kilograms cancel, newtons cancel. I'm left with coulombs. I get 600 divided by 150. So 600 divided by 150 is 4. So my answer here is 4 coulombs. So now an evaluation. Is 4 coulombs a reasonable charge? And I'm going to say something that's a little bit counterintuitive here. I'm going to say that 4 coulombs is way too large a charge for an object to have. Remember, in this class, all of the charges that we're looking at most, are microcoulombs, or 10 to the negative 6 coulombs. We almost never see whole coulombs of charge outside of an experiment, outside of something that we've done purposely to create a tremendous amount of charge, outside of experimental conditions. However, the fact that this is a tremendously large charge actually makes me think my answer is reasonable. And that makes this look reasonable. Because have you ever seen this happen? Have you ever seen something out just floating, suspended in the Earth's E field? Because I've never seen this happen. So we are unlikely to get this amount of charge, which means this process is unlikely to happen. And I've never seen it before. So I would expect it to take a tremendous amount of charge. To accomplish this. But again, we'd like to be a little bit more specific than this. So one thing that I could do is, what is actually the charge on the Earth in this example? So we are told that E at the surface is 150 newtons per coulomb. I can actually calculate what the charge on the Earth must be in order to get that E field near the surface. So here, I'm going to treat the Earth as a point-like charge. So that is my Earth, and I'm looking at the E field at some distance away from it, where that distance is the radius of the Earth. So that R is, I want to say 6.3 times 10 to the 6 meters is the radius of the Earth. Let me just double check that. Radius of Earth, 6.371 million meters. So yeah, I can round and say 6.4 times 10 to the 6 meters. So if we're treating this as a point charge, we can say E is equal to K Q over R squared. So E is K Q over R squared. We're solving for Q. So Q is ER squared over K. We can plug in our numbers. The charge on the Earth is 150 newtons per coulomb times 6.4 times 10 to the 6 meters squared divided by 9 times 10 to the 9th newtons meters squared per coulomb squared. Meters squared are going to cancel out. Newtons are going to cancel out. This coulomb is going to cancel one of these coulombs. The remaining coulomb is in the denominator of the denominator, so that's going to come up to the top. So my answer will be in coulombs. And now I just need to actually do that calculation and see what I get. So that is 150 times 6.4 e to the 6 squared divided by 9e to the 9th. And in order to get this, I get 6.8 times 10 to the 1, 2, 3, 4, 5. So that's the amount of charge that we would need on the entire Earth. So that's about, let's be generous and say that's 700,000. So I'm rounding because this is evaluation. My numbers don't need to be precise. So we have 700,000 coulombs on the entire Earth compared to the 4 coulombs I would need on me. So 7,000 coulombs on the Earth compared to 4 coulombs on me. For reference, the mass of the Earth is it 6 again? I think it's 6. 6 times 10 to the 24 kilograms. And the mass of me, I said it was 60. So it's 6 times 10 to the 1 kilograms. So look at the massive discrepancy in the masses, and look at how relatively close the charges are. So if the Earth has a charge like this charge on me is way, way small, or it's way, way bigger than I'd expect. So this is a comparatively huge charge, which again supports my understanding that this isn't a thing that normally happens, which makes it reasonable, again, because this never happens. So this is not the only way that you have to evaluate it, but again, what I'm looking for when your evaluation, it's not just simply rationalizing your answer. You actually have to put work into this evaluation to show that you have thought about contextualizing these numbers and saying if they make sense. So there is one part of this that I left out. We say that the charge is 4 coulombs. However, I haven't given the magnitude. Is that a positive 4 coulombs or a negative 4 coulombs? Well, let's look at our field lines that I drew in my sketch. If I were a positive charge, then the force would be in the same direction as the E field lines, so I'd be pulled down. However, in order for me to be suspended, the electrostatic force has to push up. So my force has to go in the opposite direction of the field lines. So that tells me that my charge has to be negative. So I can say my charge would have to be negative 4 coulombs. And that's where I'm going to leave it. All right, thank you.